embarrassing. All right. Okay, let's try that again. So we're going to go over this analogy of currents and voltages. So current is analogous to flow of liquid, flow of water. Voltage is equivalent to pressure of water, and resistance is equivalent to restriction of water. So if you take some examples, let's do a fire hose. Does this have high current or low current?
High current.
Right, good. Simple. High current. And what about the voltage? Right. High voltage, so it's got high voltage. High voltage, high current. And what about the, let's say, a squirt gun? Squirt gun. What do we got there? High what?
Pressure, which is voltage.
Right. So, but is it as much voltage as a fire hose?
No.
No.
Oh, I'm sorry. High current. No, wait.
No.
High voltage.
It's got medium voltage. So we could say medium volts. And what about current? Low current. Okay, good. What about a water jet? You guys know what a water jet is? It's a machine that can cut through aluminum or any other metal with a stream of water.
Oh, so that's very low current.
Right. And you saw those panels that we have at the shop that make up the inverter box? Those are water jetted. So it's super precision water jet.
I don't get how that works. How can water be so fast that it cuts through metal?
Well, yeah, we'll have to. It's pretty amazing. We should watch some videos on it and see how it works. So water jet, it's low current because there's not a lot of water flowing, but boy, is it high voltage, and it'll cut right through anything. So, oh, that's not an eraser. High voltage. Okay, now that's just part of that analogy. Let's talk a little bit about what happens in air if you have high voltages that get really high. And we will see some pictures of that. Hold on a second here. So here's some pictures of, hold on a second, here's some pictures of a device called the Tesla coil, which produces extremely high voltages. And that's what it looks like when you start getting high voltages in air. Pretty spectacular. Yep, Tesla invented this.
Yeah, huge one out on a mountain somewhere.
He did have a huge Tesla coil.
People like 5 miles away in a village would see lightning flash as if lightning was flashing in the mountains.
So just to be clear, a Tesla coil, we talked about AC and DC already, right? Tesla coils are AC high voltage, so electrons are flowing both directions in those discharges, but another device called a Van de Graaff generator makes DC electricity. It also makes people's hair stand up. It's not as spectacular, but anyway, there's a Van de Graaff machine making a spark. That's a direct current spark.
Is it due to friction?
Well, not really. Okay, so let's bring up one more concept, and then we're going to stop. Here's our electrical circuit. Here's our resistance, and let's say this is a 1 ohm resistor. So the current is going to be 12 amps in that wire. Okay? We want to know how much power is being dissipated in the resistor. So there's a couple different ways to figure this out. There's two equations for power. And we've learned a little bit about power in the class already in different topics. When we talked about work, we talked about how much energy, which an energy is measured in joules, and power is joules per second. So if it takes 1 joule, or let's say it takes 10 joules to raise a physics book from your table to holding it up a meter off the ground, it would take, you'd be doing that every second. You'd be dissipating 10 watts. So a joule per second, the unit is watts. Okay? So the power getting dissipated in a resistor, there's two ways to measure it. You can measure I squared times R is power, or you can measure I times V is power. And let's see if that holds true for this circuit. Let's do the first equation. So I squared, 12 squared, times R equals what? What's 12 squared? 144. 144 watts. Let's do the other one. The current, what's the current going? Let's do this one now, IV. What is power? What's the current? 12 amps. What's the voltage across the resistor? 12 volts. What's the power? 144 watts. Okay, so the power is the same because the equations work. Okay, there's a reason they work. And if anybody can tell me why they work, I'll give them extra credit. So anyway, those are the equations for power. Let's use a common example of this. So now we're going to use AC voltage, and this is the symbol for an AC voltage. And this is 120 volts. Now, you don't need to do anything different than when you're analyzing a DC circuit to use AC voltages. What we're not talking about is what the peak voltage in the circuit is. When we say your outlet is 120 volts, that is something called, so we said this is 120 volts. That's what comes out of your outlet. If you stick a voltmeter in your outlet, it's going to tell you 120 volts AC. What that really means is 120 volts RMS. Now, this means root mean square. It's a way of finding something like an average. We're not going to talk about it right now. All it means is the actual peak voltage is somewhat higher than 120. But this is a standard way of measuring it. And it works for the equations. So don't worry about the fact that this is an AC voltage. We'll just say it's 120 volts. It might as well be DC, but the reason I'm saying AC is this time our load is going to be a lamp. That's supposed to be a coil with a ball around it. That's the symbol for a lamp, and it's the same as a resistor. Okay, and so let's say this is a 100 watt light bulb, 100 watts, and you want to know what's the current I in your circuit. How do we figure that out? What was one of the equations for power we could use to figure this out? Not I squared V, P equals IV. It's I squared R, And we don't know the resistance, but we do know the power. So we're going to use P equals IV. So 100 watts. What's the current? No, we don't know the current. Sorry, we're trying to find the current. What's the voltage? 120. So 100 divided by 120. 10 divided by 12, or 5/6. What's it going to be in? Do we know? Do we know what that's going to be? 0.8, something like that. 0.8 amps. If we did our math right. I think that's what it is. So that's one way to use this power equation, and it's kind of an everyday example. So do the assigned reading and look at the different online things that I will post, and we will have a lab where we'll actually do some stuff with resistors and lamps and switches and stuff like that. So this is kind of an introduction to electricity. All right.